Welcome to this explainer. So you look around, everything feels totally solid, right? Predictable. But then you keep hearing these wild stories about particles existing in two places at once. Well, you're in the exact right place. Today, we're taking a microscopic journey to bridge that gap between everyday physics and the frankly bizarre quantum world. Don't sweat the complex science. We are going to break this whole universe down into 5 super manageable chapters. The two worlds of physics, the double slit mystery, superposition and Schrödinger's cat, spooky action at a distance, and finally, the quantum real world. Let's dive right in. Starting off with Chapter 1, the two worlds of physics, classical versus quantum. Okay, let's start in the macroscopic world, the one you and I actually live in. Think Newton, Galileo, the classics. Classical physics is that reliable set of rules that explains, why your coffee actually stays in your mug, how you throw a football, or exactly how the Earth perfectly orbits the sun. It is all about determinism. If you know the forces at play, you can perfectly predict the path. It runs just like clockwork. But when we shrink all the way down to the atomic and subatomic levels, talking electrons, photons, Newton's trusty clockwork universe, it completely breaks down. We enter this wild realm of unpredictable glitches. In quantum physics, you literally cannot say exactly where an electron is. You can only calculate the probability of finding it there. And hey, it's not a flaw in our microscopes. It's just how nature actually works at that tiny scale. Looking at this comparison, you can clearly see how the strict, totally predictable rules of large objects morph into this strange world of quantized energy and probability clouds. And take a look at that bottom row, because this is huge. In classical physics, just looking at an object doesn't change it. But in quantum physics, the very act of observing actually changes the state of the system. Crazy, right? Which brings us right to Section 2, the double slit mystery. Or, as I like to call it, the experiment that broke reality. All right, so let's look at this famous glitch in the Matrix. Imagine you're throwing tennis balls at a wall with 2 vertical slits. Naturally, you'd expect 2 piles of balls to form on the other side. Simple. Now, imagine dropping a stone in water and letting the ripples pass through those same slits. The waves overlap and they create this striped, zebra-like interference pattern. Still simple enough. But here is where it gets incredibly weird. If you fire single electrons through the slits one by one, they astonishingly act like the water waves. They create stripes. They literally seem to interfere with themselves. But wait, step 4. If you add a camera to simply watch which slit the electron goes through, the stripes completely vanish. The pattern immediately collapses back into 2 simple piles, just like those tennis balls. This mind-bending result perfectly illustrates what we call wave-particle duality. When absolutely no one is watching, particles behave like a spreading wave of possibilities. But the very second you try to observe them, you, the observer, actually alter reality. You force that wave of possibilities to collapse into one single physical particle. It is literally as if the universe is waiting for you to ask a question before it decides on the answer. This whole double slit anomaly is so fundamental to everything bizarre about the quantum world that the legendary physicist Richard Feynman crowned it the only true mystery of quantum mechanics. And honestly, decades later, we still do not fully grasp the actual mechanics of why observation collapses that wave. Moving on to Section 3, superposition and Schrödinger's cat. Dead, alive, or both? Building on that massive mystery, let's look at what happens when no one is actively looking. Back in 1935, Erwin Schrödinger came up with a famous thought experiment. Imagine a cat placed in a completely sealed box. Inside that box is a radioactive atom with exactly a 50% chance of decaying and releasing a deadly poison, and a 50% chance of doing absolutely nothing. So here's the big question. Before we open that box to check, what is the exact state of the cat? Well, according to the hardcore math of quantum theory, until you crack open the box and force a measurement, the cat exists in a bizarre state called superposition. It is simultaneously dead and alive. Think of it kind of like a rapidly spinning coin on a table. While it's spinning, it's this blur of both heads and tails at the exact same time. It only officially becomes one or the other the very moment you slap your hand down to stop it. Now, physicists are actually still intensely debating what this truly means for our reality. Does human observation directly collapse the wave function, like the Copenhagen interpretation suggests? Or, as the many worlds theory argues, does the entire universe literally split into parallel realities every single time a quantum choice is made? Or maybe it just collapses spontaneously on its own as objects get larger. The simple fact that we still don't know for sure is exactly what makes this whole field so incredibly captivating. All right, Chapter 4, Spooky Action at a Distance, Telepathic Particles. If superposition wasn't weird enough for you, let's talk about how two quantum particles can interact across the entire universe. Albert Einstein famously despised this next concept. He argued that if particles could communicate instantly across vast distances, it would completely violate his theory of relativity and the universal speed limit, the speed of light. He mockingly called it spooky action at a distance, totally convinced that quantum mechanics had to be missing some hidden variables. To really grasp Einstein's issue here, think about sending a left shoe and a right shoe in the mail to two totally different cities. When you open one box and see a left shoe, you instantly know the other one is a right shoe. But that's not spooky, right? The outcome was predetermined the whole time. Entangled quantum particles, however, are more like fuzzy magic socks. They don't actually possess a color until the exact moment you open the box. Measuring one sock instantly forces the other sock to become the opposite color, even if it's sitting all the way on Mars. So, the crucial takeaway here is that this is genuine quantum entanglement. Despite Einstein's absolute skepticism, decades of brilliant experiments testing a mathematical formula called Bell's inequality have proven him wrong. This instantaneous, almost telepathic-like connection between particles is a genuine, heavily proven feature of our universe. They aren't carrying some hidden pre-written instructions, they truly coordinate their states completely instantaneously. Let's bring it all home with Section 5, the quantum real world, from theory to technology. So it's time to zoom back out to our normal macroscopic reality. You might be sitting there thinking, okay, cool, but what does this actually mean for me? Well, without a deep understanding of wave-particle duality and entanglement, our modern world simply would not exist. We wouldn't have the internet running through fiber optic cables using lasers. We wouldn't have MRI scanners saving lives in hospitals, or those tiny transistors powering the smartphone you're probably holding right now. And looking to the near future, we are rapidly developing quantum computers that use qubits, which can actually be 0 and 1 at the exact same time, to solve incredibly complex real-world problems in just a matter of minutes. Think of quantum physics as the ultimate Lego set of the universe. Everything that feels perfectly solid around you, your desk, your morning coffee mug, literally your own body, is built entirely from these probability-based, wave-like quantum Lego blocks. The strange, unpredictable rules of the microscopic world essentially average out to create the sturdy, reliable reality we interact with every single day. And you know what's truly amazing? You do not need a massive, multi-billion-dollar underground laboratory to see this behavior in action. You can actually test wave-particle duality in your living room today. If you just grab a simple, low-power laser pointer, tape a single strand of hair perfectly straight across the beam, and shine it at a blank wall in a dark room, that hair acts just like a double slit. You will literally see the wave interference pattern of light right there on your wall. Seriously, try it out tonight. As we wrap up this explainer, I want to leave you with a final, slightly mind-bending thought about the observer effect we've been talking about. In a universe where particles literally exist only as probability waves until they are physically measured, we kind of have to ask, how much of the rock-solid reality you experience every single day only exists in that definite state, simply because you happen to be looking at it? It is a question that keeps physicists awake at night. And honestly now, hopefully, it'll keep you awake too. Thanks for joining us on this journey.